Greetings from IIT Bombay Master OT. We are an all-student team of over 40 undergraduate students from across various departments. This year, to address the challenges of URC 25, we present to you our latest iteration, Amaran, which has enhanced manipulator and traversal capabilities, robust electronic and autonomous systems, and reliable life detection modules.
This year, we have designed a 5 degree of freedom robotic arm that utilizes a linear-based mechanism which simplifies its workspace and aligns it to the task space. To actuate the links of the robotic arm, we have utilized a cycloidal gearbox with a gear ratio of 25:1 that minimizes backlash and improves precision. In the event of a power failure, to prevent backdraft of the gearbox, we are using electromagnetic brakes.
The arm features a novel differential mechanism in wrist to provide 2 degrees of freedom in a compact space. Worm gears are used with the wrist DC motors to prevent backdraft.
The gripper is incorporated with a 35 kg/cm high-torque servo motor for effective gripping by specially designed gripper links for opening a drawer, lifting and placing a 5 kg cache inside, closing the drawer, flipping switches, press the push button, unlatching and opening a door, and autonomous typing on a keyboard.
This year, we completely redesigned the Rover with significant improvements in the mobility subsystem, like transitioning from the rocker bogie to the Opus reverse 4-bar linkage, which is the ORC suspension. To refine this, we conducted extensive kinematic and dynamic simulations on MSC Adams to iterate over the link lengths for minimizing the torque acting on the wheels, which improves the stability and traction over rugged terrains. Our differential assembly ensures that the load acting on each wheel is uniform. This helps us for maintaining precise turning control and maintaining sturdy ground contact.
The drivetrain is based on a custom bevel gear assembly to reduce load on the motor shaft. It provides a reduction ratio of 2:1 to our DC motors with a RPM of 180. The assembly has been made more robust by mounting the driven shaft on 2 ball bearings. We have reduced the weight of our wheels by 55% and have optimized the browser pattern for seamless traversal across various terrains. The chassis has been optimized for a low center of gravity and modularity. Through extensive simulations, our Rover is capable of traversing various Martian-like environments.
This year, the electronic subsystem focused on reliable data transmission, acquisition, and easy-to-use controls. We transitioned to CAN architecture for actuator control and encoder feedback, which ensures high noise immunity and enhances scalability. We have implemented decentralized low-level controllers for enhancing closed-loop control and to facilitate easier debugging. We achieve precise velocity control of our end effector by utilizing a high-level resolved rate motion controller implemented on ROS2.
The Rover runs on a 12-volt lithium-ion battery, providing 120 minutes of runtime. High-precision regulators filter this voltage, and a ripple-free 5-volt powers the logical components. This year, we improved GPS accuracy using RTK with an RD simple receiver at our base station, achieving approximately 1 cm precision. For communication, an omnidirectional Rover antenna and a sector antenna at the base enable long-range connectivity even in non-line-of-sight conditions. A 5 GHz point-to-point bridge and a router ensure seamless network access.
For the gripper video feed, we used 2 FPV cameras and a digital camera mounted on a custom 2-axis gimbal, balancing low latency with high video quality.
In our autonomous tasks, we have leveraged key insights from past URC missions to enhance our system's efficiency and reliability.
This year, we developed an automated pipeline that seamlessly scans GNSS coordinates and logs them directly into a CSV file, minimizing manual intervention for faster and more accurate data processing.
For navigation, we use an extended Garmin filter to fuse IMU and GNSS data from the INS module with wheel encoders and visual odometry for precise localization. Behavior trees enable modular and adaptive decision making in dynamic environments. This year, we integrated a Z2 camera and lidar to generate an occupancy reducing SLAM. Using this, we create cost maps for real-time path adjustments, obstacle avoidance, and recovery behaviors for handling unblocked paths. We have extensively tested our system in Gazebo, ensuring the rover can effectively search for and approach Aruko markers and objects while avoiding obstacles.
After obtaining the Z2 feed, we leveraged the NVIDIA Jetsons GPU cores for real-time processing. These frames are fed to a convolutional neural network for efficient object detection.
This year, for the science mission, we have chosen to revamp our entire system to reflect competition requirements and our growing progress. Our rover conducts investigation and documentation of sites which are selected via panoramic images and stratigraphic profiling. Inside each biomodule, we conduct testing for pH, DNA, proteins, and metabolic activities within cells. This helps us gauge the possibility of life within the sample.
On finding a favorable site, we use our drill to collect soil from over a depth of 10 cm to be collected in our cache, which can be dropped off later at the base station. We also include moisture and temperature sensors on our rover, which take the respective readings from soil at a depth of 10 cm or more.
In the upcoming months, we will test our rover across various competition simulated environments. Master team IIT Bombay is excited and ready for URC 25.